I'm very, very honored to be here today because we had great speakers, outstanding scientists around the world, and I feel honored to be here talking to you today. So I'm going to be talking about a little bit about our work with metal complexes as photoluminescent probes. It's kind of like a tale of metal, lights, and time. So let's see how it goes. So my lab basically is divided in two very big groups. One group work with nanosensors and nanomaterials, and another group work with biosensors. And we basically work with anything that is related with nano, so carbon nanotubes. But basically what we do is that we have learned how to disperse carbon nanotubes. Instead of using surfactants in water, we use metal complexes, and then we basically use those metal complexes to do photoinduced electron transfer reactions for energy conversion. We also, instead of dispersing nanotubes in water, we can disperse nanotubes in materials. So for example, here we can disperse carbon nanotubes on the surface of mesoporous materials, and then load those mesoporous materials with photoactive species, in this case metal complexes, and then do photoinduced electron transfer reactions from the core of these particles to the surface of the particles. Since we have been able to do this to cover particles with carbon nanotubes, well, we thought that we could be able to do or to make transparent electrodes. So basically we are able to cover quartz with a very thin film monolayer of carbon nanotubes, and depending on the density of that film, then you can have very high photoluminescent material if you have very low densities, and if you have very high densities, then the material become more and more conductive. So you can tune the properties of the material depending on the density of the nanotubes on the surface. We have also been working on graphene, for example, graphene dope with europium and terbium, and graphene quantum dots in which we cut carbon to make small domains of carbon that acts actually as quantum dots. And lately we have been interested in making carbon nanotube liquid crystals. So if you increase the concentration of carbon nanotubes enough, then you can create very nice liquid crystal solution. If you extrude those liquid crystal solutions into a coagulating solution, then you create fibers. Very, very strong fibers, more than 250 megapascals in strength, Young modulus of more than 30 gigapascals. So extremely long and strong fibers. But today I'm not going to talk about any of this. So what I'm going to talk about today is about photoluminescent probes. So let me tell you a little bit about photoluminescent probes. So basically, you have a probe that it is not photoluminescent in the absence of the analyte, but when you put an analyte and you see the analyte coming, it's coming, and it's going to bind to the probe, and then it's going to become photoluminescent. So when the probe becomes photoluminescent, if you take the spectrum, you will see an increase in the photoluminescence, and that increase in the photoluminescence in this case is 20 times. So this 20 times in photoluminescence increase is what we call the signal to background ratio. We're going to be using signal to background ratio a lot during this presentation. So, but what I would like to convince you about today is that there's a lot of information in fluorescence spectroscopy that you don't get for a simple steady state experiment. And the students that have been taking my class will recognize immediately that this is a steady state fluorescence experiment. And here I want to introduce you to thioflavin T, one of the molecules that we use all the time in our lab, completely organic. And here is ruthenium bis BP DPPC, another molecule that we use all the time in our lab, but this is completely inorganic. And as you can see, the fluorescence spectrum of these two molecules is very similar, apart from the energy of the transitions here for thioflavin T that are shifted to the blue. The two spectra look pretty much the same. But if you add a third dimension to this plot, now if you add the dimension of time, then the picture is completely different. So let me show you. So this is a three-dimensional representation of these same molecules, but now the fluorescence spectrum is in this axis. You can see that here it says wavelength. And now this axis has the time on it. So immediately you can see that thioflavin T have a very, very short time or lifetime, while ruthenium, bis, BPD, PPC have a very long lifetime that decay relatively slow. So just to show you again, if you slice this in this direction, you get spectra. If you slice this three-dimensional plot in this direction, you get time. So here is a story about metal complexes, energy, and time. And that's what we're going to be talking today about. So let me show you the techniques that we are going to be covering. Basically, the technique that we are trying to push forward together with time result spectroscopy is what we call time gating. So let me ask students here, do you watch television, anytime? Hopefully very late in the night because you spend most of your day working, right? You say yes because your advisors probably are around. So when I was a grad student, actually, I would like to watch TV, but of course I was working most of the time. By that time, we used to have something that probably you don't know what it is, but we call the VCR. Do you know what a VCR is? Do you know what a VHS is? It was a machine that was like this big, and it has a cassette. Yes, a cassette that you put inside, and then you can record things on the TV. And then you can take that cassette out and put another one and keep recording. But the thing is that that thing will allow you to record programs. I think that nowadays we have more modern things like DVRs or stuff like that digitally record programs. So anyway, the thing is that when you watch a TV program, what is the thing that bothers you the most when you're watching something? You're watching a program, and then when something very exciting is going to happen, what happens? Is it different in Brazil? Because in the United States, exactly when something exciting is going to happen, commercials. Then you have to sit over the commercial and wait. And then when it starts somewhere else. So the exciting things happen later. With fluorescent spectroscopy, fluorescent microscopy, and fluorescent detection, we also have something like that. We don't have commercials, of course, but we have what we call noise. In the case of TV, the noise is the commercials. It's the thing that we don't want in our programs. So if you record your program, like in a VCR or a DVR or something like that, then when the commercials come, you can fast forward them and you don't see them, right? It is a way of basically eliminating noise from your program. Well, in our case, we can do the same. We can record fluorescence in time. So instead of having a picture like the steady state that I show you here, we have mostly a movie. So we can go backward and forward with time. It's kind of like a time machine. So, and as you can see, many times in fluorescence spectroscopy and in fluorescent microscopy, you get what we call autofluorescence. Autofluorescence comes from many components of a cell. Autofluorescence comes from many impurities in your sample. And autofluorescence generally is very, very short-lived. So if you have probes that live very long, for a very long time, then you can fast forward your experiment and don't take any of the autofluorescence that decreases your signal to background ratio, and then take your measurement later in time. It kind of like sounds logical, right? One of the things that we discovered is that people used to take everything, wait for the autofluorescence to decay, and take everything all the time after the autofluorescence to do the assays. What we discovered is that that is the worst thing that you can ever happen, that you can ever do, and I'm going to show you why. So don't get scared with this. This is just very simple equations. The way that you calculate the signal to background ratio is that you divide the signal of your probe plus target by the signal, divided by the signal of the probe itself. So basically, if you do it in time, it's an exponential decay, or in this case, a multi-exponential decays, because many molecules have multi-exponential decays. But this is in the theoretical case. In the actual case, when you do this experiment in the spectrometer, you have to add a new constant, which we call y. And you might ask why, and I will tell you that it is because you have always a non-specific background due to dark noise, dark counts, light percolating into the system, many things. Well, if you do the theoretical simulation using this equation and input this equation here, then you will get a three-dimensional matrix. So this three-dimensional matrix tells you that the signal to background ratio, as you start moving in time, increases, it reaches a maximum, and then start decreasing. So if you take your measurement from here all the way down here, you degenerate your signal to background ratio. So the best way, or the best thing that you can do, is to take just this part here, which is when your signal is maximum. So let me show you what I mean with that. So for that, or to demonstrate that, what we did was to develop, or to construct this kind of like probe that we call molecular beacons. It actually got the cover of Analytical Chemistry last year. And a molecular beacon is a DNA strand, basically, and it is self-complementary in the corners. So basically, it closes on itself. And it has a dye in one end of the strand and a quencher in the other end of the strand. So what happens is that you have a dye that is fluorescent, and you expect to excite the dye and get fluorescence from the dye. But what actually happens is that the quencher being so close, then you get energy transfer from the dye to the quencher, and that energy is released as heat. So basically, you really don't get any fluorescence, you basically get background. But if you add your target DNA hybridized to this part of the molecular beacon forms a double-stranded DNA, it opens up, and then the dye and the quencher are at opposite sides of the DNA strand. So now if you excite the dye, you get emission from the dye and a huge increase in emission. Now the dye is not quenched. So we synthesized a lot of these molecular beacons. We put iridium compounds with black hole quenchers, or iridium compounds with organic fluorophore like Psi5, or ruthenium compounds with the same black hole quencher and Psi5. So I'm going to show you just one example. But here it is. Here we have ruthenium with black hole quencher. And you can see this closed molecular beacon is here. The open molecular beacon that is detecting target is here. You see an increase in fluorescence. That's a signal to background ratio of 8.2. So an increase in the signal of about 8 times. That is a horrible molecular beacon. You don't want to have a molecular beacon like that. Actually, the rule for molecular beacon is that you want a molecular beacon that have a signal to background ratio of 10 or higher. So this is the bad molecular beacon. But the question is, can you improve this molecular beacon? And the answer is yes, you can do time gating. Because you can see that the background is very high. It has some impurities that are coming from here. All these things can be cleaned out if we use time gating. So basically, we did the analysis that I showed you before, not three-dimensional, because here it is not necessary. But we basically take the curve of the molecular beacon with target and divide it by the curve of molecular beacon without target, and we get this here. So this is the signal to background optimization curve. And as you can see, as you move in time, you get to a maximum about from 60 to 140 nanoseconds. And then if you keep moving to the right, you're not getting better, you just get worse and worse. So if we choose this window, then this is what you get. Don't you think it's beautiful? Basically, you don't get any of the background, any of these impurities or scattering are just gone. Now you get the spectra, or just the molecular beacon without target and the molecular beacon with target, and the increase in signal to background is about 2-fold. So that is really outstanding. So we did other experiments, I mean many other experiments, but in this case we took different ranges. So for example, right after the pulse, all over to 500 nanoseconds, or slightly in a slightly shifted time gate or the right time gating. So if we take the whole range, we see that we only get a signal to background ratio of 3.7. If we get the slightly bad time range, we get a signal to background ratio of 6, which is better. If we get the optimum, we get a signal to background ratio of 7. And there are other things happening here for this molecular beacon because we put a lot of impurities there. So the signal to background ratio at the beginning was 1.37. So we really improved the signal to background ratio from 1.37 to 7.1 by using time gating optimization.